now we want to consider coloring on planar graph. So one of the most well-known problem in graph theory, as well as maybe it's one of the very well-known problems in mathematics, is the four-color problem, or now it's known as four-color theorem. So this question was first suggested in 1852. The question is simple. So when we have a map, you have lots of country, and some country looks weird way, the other country looks another way. And it's natural to give different colors to the country so that the adjacent, country gets different color. So if these two are different country sharing a border, and if you give the same color, then it's confusing whether they are same country or not. So we want to color them in a way that if two countries share a border, then they get different color. On the other hand, if they don't share a border, this and this, we can give the same color. And people have tried and then try to determine what's the minimum number of colors needed to complete this task. And of course, we don't want to use too many colors. We want to do it efficiently. How many colors are sufficient? And empirically, people have tried lots of maps, and then all of them, it could be completed with four colors. So question is that does four colors suffice? Do four colors suffice? In 1879, which is like 27 years later, after the question was raised, Kempe published the solution. Showing that the four color is enough. However, later in 1890, after 11 years, he would publish a paper which points out that Kempe was wrong. Kempe's proof was wrong. And after that, it took quite a time until it's actually proved, which was proved using the computer assistant. And it was, maybe we will talk about that later. It's more than 100 years later, the question was raised. People had proved, apparent Haken proved the problem and showed that the four color is sufficient. But that required lots of computer work. Anyway, so this is equivalent to the following. So if you have a map, you can consider each country as a faces. And then, all the curves are the edges. And then the points which more than 3 curves meet, you can consider that as vertex. Then this gives us a graph, and then you consider its dual graph. In this dual graph, each vertex corresponds to the face. Then it's easy to check that the finding vertex coloring, proper vertex coloring in this dual graph is same as finding the face coloring. The original problem is equivalent to color this, find the vertex coloring of this dual graph. And this dual graph is planar. So it's easy to actually check that what it's asking is that if G is planar, then its chromatic number and must 4. And indeed, when Hewitt pointed out that Kempf's proof was wrong, he actually corrected the proof. But with the corrected proof, you can get a weaker bound. So it's a most 5. So let's first see how Hewitt's proof is. How Hewitt's proof goes. Before that, let's define this concept. We say that the K-chromatic graph G is, we say it's K-critical if every proper subgraph G is K-1 color. Okay, then what's easy to see is that every K-chromatic graph contains a K-critical subgraph. Of course, if you have a K-chromatic graph, you delete an edge and see whether the chromatic number changes. So you have G, and then you consider the deletion of every possible edge, and none of them decrease the. So if you choose an edge and then you delete an edge, and then chromatic number does not decrease, then you delete. And you do the same, you repeat it. Whenever there is an edge whose deletion does not decrease the chromatic number, you delete it until you cannot. Then you are ending up the situation that you have a K-chromatic number, K-chromatic graph, and then deletion of any edge give you a lower chromatic number. So those subgraph are K-1 colorable, then that's your K-critical graph. So that's the basic elements for this K-chromatic graph. So K-critical graphs are the basic elements which ensure the graph to be K-chromatic. The study about this will give us an understanding on the K-chromatic graph. And one of the facts that needed to see is that the K-critical graph satisfies that its minimum degree is at least K-1. If not, if you have a vertex whose degree is less than K-1, then what? This is K-critical, so this can be colored with K-1 colors. And then, now you can extend this coloring by giving the color of this, which is different from colors of all its neighbors. The number of neighbors is smaller than K-1, so one available color remains here. So that's easy to see. Okay, with this definition, now let's see how he would prove that every planar graph is bicolor. So it's sufficient to every planar graph, if you consider its subgraph, it's also planar, right? So it's suffice to show that no planar graph is 6 critical. If there is a planar graph which has chromatic number 6, then it must have a subgraph which is 6 critical graph. That's also planar graph. So if we show this, then that automatically shows that the planar graph is bicolor. So let G be a 6 critical planar graph. then we know that its minimum degree at least 5. But what do we know? We know that every planar graph on n vertices satisfy that its number of edges is m mod 3 and minus 6. So that's what we showed last time. And then that shows that average degree is m mod 6 and minus 12 over n, which is smaller than 6. So that means there must be a vertex of degree m mod 5 in any planar graph. In other words, any planar graph is 5 degenerate. So this alone already gives you that every planar graph is 6 colorable. That's, weaker than what we want to show, but that's very natural bound. Anyway, so any planar graph is 5 degenerate, and then this planar graph has minimum degree 5. So what? This implies a minimum degree of G is exactly 5. There exists V with the degree exactly 5. So let's take such a V. Then it has 5 neighbors. Let's say V1, V2, V3, V4, V5. So now consider, because this is 6 critical graph, deleting the remaining graph, you can color it with the 5 color. Consider coloring or bi-coloring of G minus P. And then we may assume that let's say this coloring is F. F of Vi is I. We can assume that. Why? In this coloring, everything is colored except V. And what we know is all 5 colors must appear on this neighborhood of V. If not, if only 4 colors appear, then we use the remaining color to color B, then which completes the 5 coloring of the entire graph G, which is contradiction as we assume that G is 6 critical. So all 5 colors appear here. So, by changing the name of the colors, we assume that this has color 1, 2, 3, 4, 5. Okay, now what we want to do? What we want to do is we take, say, this vertex of color 2. And then let's say you take its neighbor of color, say, 4. If there are no neighbor of this vertex with the color 4, then what we can do? We can simply recolor this with 4, and then we can color B with 2, which would complete the coloring. That means that this vertex must have a neighbor of color 4, and so on. If this one does not have another vertex with color 2, then again we can switch this to 2, this to 4, and then we can color 2. So that's basic idea on how we want to proceed. So for this, so we let Gi J be the subgraph of this G minus B, which are induced by the vertices of color I and J. That's right, you are taking this vertices of color 2 and 4 here. You consider all the vertices of color 2 and 4. Then what? If you take a component of this, and then switching the colors on a component of this Gij yields another proper 5 coloring. We switch all of them in the component. And then, subject is component. That means that any neighbor of this, it doesn't have a color 2 and 4. So even if you switch the color, so every vertex of color 2 become color 4, and every vertex of color 4 become 2, that's still proper coloring. So if the component of Gij that contains Vi, so B, you have 5, and then here you have a color 2, say you have and then these are color 4, these are color 2, these are color 4, 2, 4. If this does not contain Bj, say here B4, then what we can do is we swap the colors here, and then now this become color 4, this become color 4, so 2 is available here. So that's possible. Then we switch the color I and J. Maybe let's say this color on this component removes the color I on the neighbor of B. Now we can give color I to B produces proper by coloring of G, which says that the is 5 colorable contradiction. So then what can we conclude? So for each I and J, the component of Gij that contains Bi must also contain Bj. So in that case, what happens? So here you have a 2, and here you have 4. So in such a case, if you swap the colors here, switch the colors here, and this becomes 4 and this becomes 2, and this is 1, 3, 5. So it's still the same 5 color rule appears at the neighbor of B. So we are not able to color this B with some other color. So this must happen because we assume that the G is not 5 color. So let Pij be a path in this Gij from Bi to Bj. So in this argument, I and J could be any pair. And now what? You have B2, B1, B3, B4, B5. Let's say they appear in this order, L clockwise order. Then what we consider? We consider the cycle. The cycle C obtained from a P to 4 and P to P. So this is the cycle. C is what? Separates P1 and P3. Yeah, I mean, this can be shown that by the Jordan-Cobb theorem. The Jordan-Cobb theorem says that this cycle separates inside and outside. And then, yeah, in here, the P3 has to be inside, P1 has to be outside. Then what? We can consider the path P2 forward again. Then it must cross this cycle C. But what do we know? Since C is planar, the passes cross only at the common vertex, shared vertices. But what do we know? The vertices of P1, 3 as color 1 and 3, and the vertices of P2, 4 have color 2 and 4, so they have no common vertex. A contradiction. And this contradiction proves the theorem. Then what it means is that at least one of G13 or G24, one of them contains a component which contains at most one of these two or one of these two, not both. Then you can flip the colors in that component, and then you can extend the coloring of a smaller graph, G minus P to G. Here you utilize the passes where the two colors alternate on the path. That's called such a path is called the Campeche. It's a path on which two specific colors alternate. Okay, then what was the Campeche's original failed proof? You do the same thing, so you have B, and then you have these 5, neighbors. And then let's say you have color 1, 2, 3, 4, and 2. So now you are using only 4 colors, and all of those 4 colors have to appear on the neighbor of B, and something has to appear exactly twice, and the rest of them exactly once. And you do the same thing. You consider P1, 3, and then P1, 4. And then what you do, here you consider the P2, 4, G2, 4. G2, 4. And then here you consider G2, 3. And then because these are cycles, so these G2, 4 and G2, 3 are inside this cycle, so they don't interact each other. And then you swap these two colors here and swap these two colors. Switch two color on this component, switch two color. And this become what? 3, and this become 4. So color 2 become available, so you color it. That's Campeche proof. Then where was it wrong? Here was proof that it is wrong, and this must be wrong. So one of the reasons why it's wrong is that the Campeche actually, neglected the fact that this path and this path could intertwine. So this is possible. So this is your P13. This is your P14. So this and this. And let's say you have an edge here. And inside here, what? You have 4, you have 2 here. Here you have 3, you have 2, you have 3. In such a situation, what? Between this 2 and 4, and then 2, 3, 3, 2, 2. What happens if you split this color? And this becomes 2 and this becomes 2, they are adjacent. So it's not giving you a proper coloring. So that's where this compact proof failed. Okay, and yeah, after a long time in 1976, Appel and Haken finally proved this four-color theorem using computer search. So we will talk about this, but before that, we discussed other things first. One of the things that we want to consider is strengthening of this theorem. Okay, it's not tight because we know that every planar graphs are four-colorable. But then what about what about least coloring? We can actually find some planar graph which is not four least colorable. So whose least chromatic number is 64. We can find the planar graph G such that this holds. Then natural question is that then what's the best upper bound on this least chromatic number for all planar graphs? And Thomason proved that every planar graph is actually 5 least colorable. For that, let's define a concept. We say that the triangulation is a plane graph. So graph with embedding, which is so it's already embedded on the surface, where every base boundary is 3 types. When you have any graph, then you can add edges until this is satisfied. Then every base boundary is 3 cycles. So in some way, this is the maximal triangle maximal planar graph. So you add an edge while it's still maximal, while it's still planar. And we say a plane graph in which the boundary of outer face, the unbounded face, is a cycle, and every bounded face is a triangle. If this happens, then we call that this is weak triangulation. On here, you just add an edge until all the bounded faces are triangle. Then the unbounded face is not triangle, but it's okay, then it's weak triangulation. And the vertices on the outer face is called the external vertices. Let's call them external vertices. Now we can prove this Thomason proof that every planar graph is 5-bit colorable, by choosable. So this is one of the case that the stronger statement is easier to prove. In induction, if you make a statement stronger and then you use induction, then your induction hypothesis gets stronger. While what you want to show is more difficult to show, but your assumption, induction hypothesis, is stronger. So it often helps you to do the induction. So we want to prove this. First, we know that adding edges does not decrease the least chromatic number. So we assume that our graph is a weak triangulation. So as long as we prove the statement for weak triangulation, then we are done. And we want to make the following stronger claim. And we prove that if this weak triangulation G has a least coloring, even when the following, you have outer vertices and the, it's external vertices and some other things inside, that's all. What's least coloring? In each vertex, a list of colors is given, and then we want to choose one of the colors for each vertex so that you get the proper coloring, right? And then in order to show that its least chromatic number is mod 5, we want to show that if every list has size exactly 5, then you can complete this coloring, no matter how the lists are given. Okay, but here we want to do even stronger. When there are two adjacent vertices, they are given a list of size 1, with a different color, of course. So there are two adjacent vertices. So that means that this has to be colored with 1, this has to be colored with 2. So it's more restricted. Two adjacent vertices on the outer face have distinct width of size 1, and the other external vertices have width of size 3, and all other vertices have width of size 5. So this is more restrictive condition, and with this condition, you can complete the list palette. So that's the claim. We use induction on n, which is the number of vertices in G. If n is 3, so that's the base case, then what? You have one vertex with the list 1, one vertex with list which is different from the other, and here you have 3 colors. Then you can color this with this color and color this with this color too. And then out of 3 colors, one of the colors must be different from this too, so you use it. So it's easy to check. The basic case is done. Now consider n bigger than 3. And consider this outer face, P1, P2, P3, P, say. So let the vertices of the outer cycle C, P1 to P in clockwise order. And with B1 and BP being the vertices with fixed color. So here we have list of size 1, and then everything here have list of size 3. So let's consider two cases. Case 1. If C has a chord Bi, Bj with its Ij are not consecutive because this is chord, and then they are between, say, identify this. So if it has this chord, then what happens? It's either this or this or this or this. Or this. It doesn't matter. But in any case, if you have this chord, then what we can do, we can partition the planogram into two, and then we complete the coloring here and complete the coloring here. And this part is smaller and this part is smaller, so we can apply induction. So then we apply the induction hypothesis to the graph induced by the cycle V1 to Vi and Vj to Vp and the vertices inside. Then what? This gives us the proper coloring of this, selecting from its list. It's the next proper coloring. In which Pi and Vj receive distinct color, distinct fixed color. Now what? Now these two are already colored. That's same as giving them a list of size 1. And then with that, you apply induction hypothesis to complete the coloring. Now we apply the induction hypothesis to the graph induced by the cycle Vi plus 1 to Vj and the vertices inside it to complete the coloring. So case 1 is done. Then what's case 2? So C has no chord. Then how does it look like? You have V1, you have Vp, you have V2, then you have V3. Then what? If V2, you consider its neighbor. Let V1 and then say U1 to UK and V3 be the neighbors of V2 in order. Then because this is weak triangulation, if this is neighbor, then they have to be neighbor, so this looks this way. P being 3 is possible here. So if V3 could be Vp, but it's okay. And this K could be, although this K is not 0, in that case you have this chord, but we assume that this is not chord. So there is at least one UI. So you have this. As I mentioned, because bounded faces are triangle G has a path P with the vertices P1, U1 to UK, P3. So this is path P. What do you know? And C has no core. U1 to UK are internal vertices, which are not the vertices that are not external vertices. And the outer face of G minus P2. So you now delete this, and then you want to apply induction on here. This is bounded by cycle C prime, in which P is replaced P1, V2, V3. So this is C prime. So that's the outer face of this, the G prime, which is G minus P2. So what? Now that C is the color assigned to P1. So let's say this is colored with C. Then what do you know? Since this list assigned on P2 as side L3, we may choose a color from this list. So the two colors, distinct colors, X and Y in this list, which is not C. Now these two colors, we want to reserve it for the possible use of coloring this P2 later. So for that, we forbid X and Y from this U1 to UK, meaning that since L of UI, they are all internal vertices, they have a list of size 5, let's say exactly 5, we have that its new list, then L prime, which is L of UI minus X and Y, have side L3. So we may apply induction hypothesis to this G prime. Now what? This has list of side 1, this has list of side 1, this has side 3, 3, 3, 3, 3, 3, 3, everything 3 here, and inside is still list of side 5. So that's exactly the situation that we can apply the induction hypothesis. So induction hypothesis to G prime, in the resulting coloring, this induction hypothesis give coloring. In the resulting coloring, P1 and U1 to UK have all colors outside X and Y. So none of these has color. None of these have colored X or Y. So X, Y is still available for P2, except this P3 might be colored. So what? We extend this coloring to G by choosing a color in X and Y that does not appear on P3 in the coloring object part. And we use that to color P2. So that will complete the coloring. So this proves that the entire graph was, parallel with this claim. So we prove this claim, and then that implies that every planar graph is 5 children. Okay, so we show that the planar graph is not only 5 colorable, but also its least chromatic number is M of 5. And then this 5 is tight. There are planar graphs whose least chromatic number is bigger than 4. Okay, so we proved that today, and then in the next video, we will discuss further about this 4-color theorem. Okay, then I will see you in the next video. Thank you.